What existed before the universe? A journey beyond the Big Bang. One of the deepest and most unsettling questions ever asked by human minds is not about stars, galaxies, or distant planets. It is a question that reaches beyond all of them. Did anything exist before the universe itself? Modern science tells us that everything we see today, every galaxy, every particle, every atom, and even time itself, can be traced back to a single moment roughly 13.8 billion years ago. This moment is known as the Big Bang. According to our best theories, the universe did not emerge into empty space. Instead, space itself began expanding from an unimaginably hot and dense state. Yet the question remains, what, if anything, came before? Was the Big Bang truly the beginning of everything? Or was it merely a transition, a chapter in a much larger cosmic story that we are only beginning to understand? For centuries, philosophers, theologians, and scientists have struggled with this mystery. Today, with powerful telescopes, precise measurements, and bold new theories, we are closer than ever to exploring the earliest moments of existence, and possibly even what preceded them. In this documentary journey, we will travel back to the birth of time, explore the oldest light in the universe, examine discoveries that challenge our understanding of cosmic history, and confront radical ideas that suggest the universe may be far older and stranger than we ever imagined. According to the standard model of cosmology, the Big Bang represents time zero, not just the beginning of matter and energy, but the origin of space and time themselves. Before this moment, the equations of physics break down. Our models simply stop working. At the very beginning, all the energy that would later form billions of galaxies was compressed into a state of extreme density. In the tiniest fraction of a second, the universe underwent a dramatic event known as cosmic inflation. Space itself expanded at a rate far faster than the speed of light, not because matter was moving through space, but because space itself was stretching. This brief but violent expansion smoothed out the universe and planted the seeds for everything that would come later. 1 second after the Big Bang, the universe was a searing hot ocean of fundamental particles. Protons, neutrons, electrons, and radiation existed in a chaotic, dense environment where nothing stable could yet form. Within minutes, the first atomic nuclei were created in a process known as primordial nucleosynthesis. Hydrogen and helium emerged, along with trace amounts of lithium, the raw ingredients of all future stars. At this stage, the universe was still far too hot for atoms to exist. Electrons could not remain bound to nuclei. Light was constantly scattered, unable to travel freely. The cosmos was filled with a thick, glowing fog. For hundreds of thousands of years, the universe remained opaque. Then, approximately 380,000 years after the Big Bang, a critical transformation occurred. As the universe expanded, it cooled enough for electrons to finally attach to nuclei, forming neutral atoms for the first time. This moment is known as recombination. With electrons locked into atoms, light was suddenly free to move through space. The cosmic fog lifted. Radiation streamed outward in every direction, carrying with it a snapshot of the infant universe. That ancient light still exists today. We observe it as the cosmic microwave background, or CMB, a faint glow that fills the entire sky. It is the oldest light we can see, stretched by billions of years of cosmic expansion in a microwave wavelengths. The CMB is not just radiation. It is a time capsule. By studying it, scientists can reconstruct the state of the universe when it was less than 500,000 years old. Tiny variations in its temperature, differences of just a few millionths of a degree, encode the earliest density fluctuations. These slight irregularities would later grow into galaxies, galaxy clusters, and the vast cosmic web. Discovered accidentally in the 1960s, the cosmic microwave background has since become one of the most important pillars of modern cosmology. Satellite missions and ground-based observatories have mapped it with increasing precision, revealing extraordinary detail. From these measurements, scientists have learned something astonishing. Ordinary matter, the atoms that make up stars, planets, and life, accounts for only about 5% of the universe. Roughly 27% is dark matter, an invisible substance that interacts through gravity. And nearly 68% is dark energy, a mysterious force driving the universe's accelerated expansion. In early 2025, researchers using the Atacama Cosmology Telescope, in collaboration with Princeton University, released the most detailed images of the cosmic microwave background ever produced. These images offered unprecedented resolution, far sharper than earlier full-sky maps. For the first time, scientists could measure not only the distribution of matter in the early universe, but also its motion. The polarization of the CMB revealed how primordial gas flowed and shifted under gravity. These observations allow cosmologists to trace how a nearly uniform universe evolved into the complex structure we see today. From tiny ripples in the early cosmos arose galaxies, stars, and eventually life. But the CMB only tells us what happened after the Big Bang. What came next? Following recombination, the universe entered a long, dark period. The background glow gradually faded, and no stars yet existed to replace it. This era is known as the Cosmic Dark Ages. Gravity slowly pulled matter into denser regions. Over tens of millions of years, vast clouds of hydrogen collapsed, growing hotter and denser until nuclear fusion ignited. The first stars were born. These earliest stars, often called population 3 stars, were unlike anything we see today. They were enormous, incredibly bright, and short-lived. Their intense radiation ended the cosmic dark ages and transformed the universe once again. Astronomers call this period the cosmic dawn, the moment when the universe first lit up with starlight. Today, humanity is finally beginning to glimpse this ancient epoch. The James Webb Space Telescope, launched in late 2021, was designed to observe infrared light from the earliest galaxies. Because the expansion of the universe stretches light into longer wavelengths, the most distant objects can only be seen in infrared. JWST has exceeded expectations. Within its first years of operation, it discovered galaxies that existed just a few 100 million years after the Big Bang, far earlier than many models predicted. In 2025, one galaxy, designated JADES GS Z14-0, became the most distant galaxy ever observed, seen as it was only about 280 million years after the universe began. The light from this galaxy traveled for more than 13.5 billion years before reaching us. Even more surprising was its brightness and chemical composition. It appeared to be forming stars rapidly, with elements suggesting an advanced level of stellar processing. This challenges long-held assumptions about how quickly galaxies could form. These findings suggest that the early universe may have evolved faster and more efficiently than previously believed. As telescopes improve, scientists hope to peer even closer to the moment when the first stars ignited. But no telescope, no matter how powerful, can see beyond the Big Bang itself. To explore what came before, we must rely on theory. On the largest scales, galaxies are not randomly scattered. They form a vast cosmic web of filaments and voids, shaped by gravity and dark matter. This structure traces its origins back to the tiny fluctuations seen in the CMB. According to the cosmological principle, the universe should appear uniform when viewed on sufficiently large scales. No region should be fundamentally different from another. Based on this idea, cosmologists predicted a limit to the size of cosmic structures. Yet recent discoveries have challenged this assumption. In 2024, astronomers identified an enormous ring-like arrangement of galaxies, known as the Big Ring. Stretching over 1 billion light-years across, it lies near another massive structure called the Giant Arc Together. These formations exceed the size limits predicted by standard cosmology. These colossal patterns are difficult to explain. They may be statistical coincidences, but the growing number of such structures suggests something deeper. Some scientists speculate that these anomalies point to unknown physics in the early universe. Others suggest they may be relics of processes that occurred before the Big Bang. One of the most radical proposals comes from physicist Roger Penrose. His theory of conformal cyclic cosmology suggests that our universe is just one in an endless sequence. In this view, the Big Bang was not a beginning, but a transition from a previous cosmic era. Penrose has even proposed that faint circular patterns in the cosmic microwave background could be remnants of events from a universe that existed before ours. While controversial, such ideas force scientists to confront the possibility that the universe has no true beginning. Another major mystery shaping our understanding of cosmic history is dark energy. In 1998, astronomers discovered that the expansion of the universe is accelerating. Something is pushing galaxies apart faster and faster. This unknown influence was named dark energy. For decades, the simplest explanation was that dark energy is constant, a fixed property of space itself. But new data is beginning to challenge this assumption. Observations from the Dark Energy Spectroscopic Instrument suggest that dark energy may not be constant after all. Instead, its influence could be changing over time, weakening as the universe ages. If confirmed, this would profoundly alter our predictions about the universe's future. Expansion might slow, stop, or even reverse. Meanwhile, dark matter remains equally mysterious. Despite its crucial role in forming galaxies, it has never been directly detected. This has led some scientists to question whether our understanding of gravity itself may be incomplete. In recent years, alternative models have emerged that attempt to explain cosmic observations without invoking dark matter or dark energy. One such idea proposes that the universe did not originate from a single Big Bang, but from multiple creation events, brief bursts of energy appearing throughout cosmic history. In this view, the Big Bang may have been only the first in a series of transitions. These temporary singularities could explain cosmic expansion and structure formation without requiring invisible substances. Though speculative, such theories highlight a crucial truth. The Big Bang model, while extraordinarily successful, is not complete. So what was before the Big Bang? Perhaps time itself began at that moment, making the question meaningless. Or perhaps the universe emerged from a prior phase, a bounce, or a previous cycle. Quantum gravity models suggest that space-time may continue through such transitions. At present, there is no definitive answer. What we do know is that the universe is far more complex and mysterious than we once believed. Each new discovery brings clarity and deeper questions. The boundary between before and after the Big Bang remains the final frontier of cosmology. And as long as humans continue to look up at the stars and ask where everything came from, the search for answers will never end. Which explanation do you find most compelling? Yet beyond equations, telescopes, and data sets, there is a deeper layer to this mystery, one that touches the very limits of human understanding. When we ask what existed before the Big Bang, we are not merely asking a scientific question. We are confronting the boundaries of logic, language, and imagination itself. Science operates by observing cause and effect, but the Big Bang challenges this framework. If time itself began at that moment, then the concept of before may not apply. Cause and effect may have emerged together with space-time, making the origin of the universe fundamentally different from any other event we study. This idea unsettles us because the human mind is wired to think in sequences. We expect beginnings to have causes. We assume that every effect must arise from something earlier. The possibility that reality itself has no prior cause feels deeply counterintuitive. And yet, nature has repeatedly shown that our intuition is not a reliable guide at extreme scales. Quantum physics already reveals a world where particles can appear and disappear, where outcomes are probabilistic rather than deterministic, and where events can be correlated across vast distances instantaneously. At the quantum level, the universe behaves in ways that defy everyday logic. Some physicists suggest that the Big Bang may have emerged from a quantum fluctuation, an instability in a deeper vacuum state. In this view, nothing is not truly empty. It is a seething sea of quantum potential governed by physical laws. Under the right conditions, a universe could spontaneously arise. But this raises another profound question. If physical laws allowed the universe to emerge, where did those laws come from? One possibility is that the laws of physics themselves evolved. In the earliest moments, the universe may have operated under rules vastly different from those we observe today. As the cosmos expanded and cooled, stable laws may have crystallized, giving rise to the predictable universe we now inhabit. This idea aligns with certain approaches to quantum gravity, which attempt to unify general relativity and quantum mechanics. These theories suggest that space-time may not be fundamental at all. Instead, space and time could emerge from deeper, more abstract structures, networks of information, quantum states, or mathematical relationships. If space-time is emergent, then the Big Bang may not represent the birth of everything, but rather a phase transition, a transformation from one state of reality into another. In this context, asking what came before the Big Bang is like asking what lies beneath the surface of water. The surface appears solid and continuous, but beneath it lies a dynamic, unseen world. Some theories propose that our universe is just one region within a much larger multiverse. In this picture, the Big Bang marks the birth of our local bubble, while other universes may exist beyond our cosmic horizon. Each universe could have different physical laws, constants, and histories. Inflationary cosmology naturally gives rise to this idea. In certain models, inflation never completely ends. Instead, it continues in some regions while stopping in others, producing countless universes over time. If this is true, then what existed before our Big Bang was not nothing, but a larger cosmic process still unfolding. However, the multiverse hypothesis remains controversial. Critics argue that it may be impossible to test experimentally, placing it beyond the traditional boundaries of science. Supporters counter that it emerges naturally from otherwise successful theories and may eventually yield indirect evidence. Another intriguing possibility is that our universe is fundamentally informational. Some physicists propose that reality is built from bits of information rather than matter or energy. In this view, the universe is a vast computational process, evolving according to underlying rules. If information is fundamental, then the Big Bang could represent the initialization of a cosmic computation. Before it, there may have been no data, no memory, no state, only potential. But even this does not fully resolve the mystery. Why does anything exist at all? Why is there a universe instead of nothing? This question lies at the intersection of science and philosophy. Science can describe how the universe evolves, but explaining why it exists may require a deeper framework, one that we have not yet discovered. Throughout history, every time humanity believed it had reached the ultimate explanation, nature revealed another layer beneath. The Earth was once thought to be the center of existence, and the sun took its place. Later, we discovered that our galaxy is just one among hundreds of billions. Now, we are faced with the possibility that our universe itself may not be unique. The story of cosmology is not one of final answers, but of ever-deepening questions. Future observations may offer new clues. Gravitational wave detectors could reveal signals from the earliest moments of cosmic history. Subtle patterns in the cosmic microwave background may hint at events that predate the Big Bang. Particle physics experiments may uncover evidence of extra dimensions or hidden symmetries. A complete theory of quantum gravity could transform our understanding of time, space, and causality. Such a theory might finally allow us to describe the universe at the moment of its birth, or even before. Until then, the question remains open. What existed before the universe? Perhaps nothing. Perhaps everything. Perhaps something so alien to our understanding that words like before and after no longer apply. What is certain is this: The universe we inhabit is not simple, not static, and not fully understood. It is a dynamic, evolving system filled with mysteries that stretch across billions of years and trillions of kilometers. And yet, from within this vastness, a tiny species on a small planet has learned to ask these questions. We have traced our cosmic origins from the first atoms to the first stars, from ancient light to modern telescopes. We have reconstructed the story of the universe back to its earliest moments. Now, we stand at the edge of the known, staring into a conceptual horizon beyond which our theories fade. The search for what came before the Big Bang is more than a scientific pursuit. It is a reflection of humanity's deepest curiosity, a desire to understand not just where we are, but why we exist at all. As long as that curiosity endures, the universe will continue to reveal its secrets, one discovery at a time. And perhaps one day, we will finally glimpse the answer to the greatest question of all. Here is a further extension, written to seamlessly continue the documentary without restarting, maintaining the same cinematic, authoritative tone, and deepening the theme to push the combined script safely beyond 30,600 characters. This section expands the future of cosmology, limits of knowledge, human perspective, and observational horizons. As we move deeper into this unknown territory, another profound limitation emerges, one that no future telescope may ever overcome. The observable universe itself has boundaries. Because light travels at a finite speed and the universe is only 13.8 billion years old, we can observe only a portion of reality. Beyond this cosmic horizon, regions of space exist whose light has never reached us and never will. These regions may contain galaxies, structures, or even entire cosmic histories that remain forever inaccessible. This means that our understanding of the universe is inherently partial. No matter how advanced our technology becomes, there may always be aspects of reality hidden beyond our reach. This realization humbles modern cosmology. It reminds us that science does not promise omniscience. Instead, it offers progressively better approximations of truth, constrained by observation and testability. Yet even within these limits, the progress made over the last century is extraordinary. Just 100 years ago, the idea that the universe was expanding was radical and controversial. Today, it is a foundational fact supported by overwhelming evidence. Similarly, concepts that now seem speculative, cyclic universes, quantum spacetime, evolving physical laws, may one day become established components of scientific understanding. Another emerging field that may reshape our perspective is quantum cosmology. Unlike classical physics, which treats spacetime as smooth and continuous, quantum approaches suggest that space and time may be granular at the smallest scales. At the Planck length, reality may resemble a foam-like structure where traditional geometry breaks down. In such a regime, the Big Bang singularity may disappear entirely. Instead of an infinite point of density, the universe's origin could be described as a transition between quantum states. This would remove the notion of a true beginning, replacing it with a process governed by probabilistic laws. Some models even suggest that time itself may be an emergent phenomenon, arising from more fundamental interactions. In these frameworks, the flow of time we experience is not universal, but local, dependent on the structure of the universe. If true, then the Big Bang did not begin time everywhere, but only initiated the particular temporal structure we inhabit. This raises an unsettling but fascinating possibility that before the Big Bang may exist in a sense completely detached from human intuition. Our language, evolved for survival on Earth, may simply be inadequate to describe such realities. There is also the question of observation itself. In quantum mechanics, the act of measurement plays a fundamental role in determining outcomes. Some physicists have wondered whether the universe requires observers in order to take on definite properties. While controversial, this idea suggests a strange feedback loop between consciousness and cosmology. Did the universe exist in a fully defined state before observers arose? Or did complexity and structure gradually become meaningful only as the universe evolved and produced systems capable of perception? These questions blur the boundary between physics and philosophy, reminding us that cosmology is not just about distant galaxies. It is also about our place within the universe. From a cosmic perspective, human existence is astonishingly recent. All of recorded history occupies a vanishingly small fraction of cosmic time. Yet within this brief window, we have decoded the light from the beginning of the universe and reconstructed events billions of years before our planet even formed. This achievement is not guaranteed. Civilizations could rise and fall without ever uncovering these truths. That we live at a time when such knowledge is accessible may itself be extraordinary. Looking ahead, the future of the universe depends on forces we barely understand. If dark energy continues to weaken, cosmic expansion could slow, potentially halting altogether. In some scenarios, gravity might eventually dominate, pulling matter back together in a catastrophic collapse known as the Big Crunch. In others, expansion may continue forever, leading to a cold, empty cosmos where galaxies drift beyond each other's horizons and stars burn out one by one. This fate, sometimes called the heat death of the universe, represents an ultimate form of cosmic loneliness. But if cyclic models are correct, then even such an ending would not be final. Collapse could give rise to renewal. Death could lead to rebirth on a cosmic scale. The universe, in this view, is not a one-time event, but an eternal process. Ultimately, the question of what existed before the Big Bang may not have a single answer. Different theories may describe different aspects of a deeper truth, each valid within its own framework. Reality may be layered, with multiple levels of description coexisting. What matters is not just the answer, but the pursuit itself. By asking what came before the universe, we are testing the limits of human understanding. We are challenging ourselves to think beyond intuition, beyond experience, and beyond the familiar structure of time and causality. And in doing so, we continue a tradition as old as humanity itself, the quest to understand where we come from. The universe may never reveal all its secrets, but with every observation, every equation, and every new idea, we move closer to the edge of the unknown. And standing at that edge, we are reminded of a simple truth. The greatest mystery of the universe is not just its origin. It is that the universe exists at all, and that within it, there are minds capable of wondering why. To move further, we must confront another subtle but crucial concept: entropy. Entropy is often described as the measure of disorder, but in cosmology, it plays a far deeper role. It defines the arrow of time itself. Time, as we experience it, flows in the direction of increasing entropy. The past is more ordered, the future more chaotic. The early universe, surprisingly, was in an extremely low entropy state. Despite being hot and dense, it was remarkably uniform. This fact is one of the deepest puzzles in cosmology. Why did the universe begin in such an ordered condition? If the Big Bang were the absolute beginning, then this low entropy state would appear almost miraculous. But if the universe emerged from a prior phase, then perhaps that order was inherited. Some models suggest that entropy was reset during a cosmic bounce, allowing time's arrow to reverse or restart. This idea reframes the Big Bang not as a moment of creation, but as a moment of reorganization. Time itself becomes a local phenomenon, tied to entropy gradients rather than absolute beginnings. In regions where entropy increases, time flows forward. In regions where it decreases, or where entropy is undefined, time may lose its meaning entirely. This challenges our deepest assumptions. It suggests that time may not be fundamental, but emergent. A consequence, not a cause. If time emerges, then the universe does not need a beginning in the traditional sense. Instead, it may exist as a timeless structure with Big Bang, like events occurring within it, much like waves forming on the surface of an ocean. Mathematics plays a central role in shaping these ideas. The equations that describe space-time, quantum fields, and gravity do not explicitly require a beginning. In many solutions, space-time extends infinitely in one direction or forms closed loops. Our interpretation of these equations depends heavily on boundary conditions, assumptions we impose because we lack complete knowledge. This means that the universe we describe mathematically may be far larger than the universe we can observe. Some physicists take this even further, proposing that mathematics itself is the fundamental reality. In this view, the universe exists because it is mathematically consistent. All possible mathematical structures exist, and conscious observers simply find themselves within one that allows complexity. If this sounds abstract, it is, but it offers a radical answer to the question of origins. The universe does not need a cause. It exists because it can. Another idea gaining attention is the simulation hypothesis. While often discussed philosophically, it has implications for cosmology as well. If our universe is a simulated system, then the Big Bang could represent initialization, the starting condition of a computational process. In such a scenario, asking what came before the Big Bang is like asking what came before a program was run. The answer exists outside the system itself. This idea remains speculative and controversial, but it highlights a recurring theme: the possibility that ultimate explanations lie beyond the universe we observe. Importantly, none of these ideas diminish the success of the Big Bang model. On the contrary, they build upon it. The Big Bang remains our most accurate description of the universe's early evolution. It explains the expansion of space, the cosmic microwave background, the abundance of light elements, and the large-scale structure of galaxies. What it does not explain is why those initial conditions existed. That gap is where modern cosmology now operates. New generations of instruments will push these boundaries further. Future space telescopes may map the cosmic microwave background with even greater precision, searching for subtle anomalies. Next-generation gravitational wave observatories may detect signals from epochs far earlier than any light can reach. Particle accelerators may uncover hidden dimensions or new fields that reshape our understanding of reality. Advances in artificial intelligence may even help identify patterns in cosmic data that human intuition misses entirely. Each of these tools brings us closer to understanding the universe's deepest structure. But there's also a sobering possibility. It may be that the question of what existed before the Big Bang has no empirical answer. Some aspects of reality may lie permanently beyond observation, accessible only through indirect inference or philosophical reasoning. If so, then cosmology faces a unique challenge. It must accept uncertainty not as failure, but as an inherent feature of studying the totality of existence. This does not weaken science. It strengthens it. Science is not a collection of absolute truths. It is a method, a disciplined way of asking questions, testing ideas, and refining our understanding. The mystery of the universe's origin is not a flaw in this method. It is its ultimate test. Throughout history, unanswered questions have driven progress. The nature of light, the structure of atoms, the motion of planets, each once seemed unknowable. Yet each yielded to persistent inquiry. There is no reason to believe the origin of the universe will be different. What we are witnessing today is a transition. Cosmology is evolving from a science of description to a science of foundations. It is no longer satisfied with explaining how the universe behaves. It seeks to understand why it exists at all, and in doing so, it forces us to confront our own existence. We are not separate from the universe. We are a product of it. The atoms in our bodies were forged in ancient stars. The laws that govern our thoughts are the same laws that govern galaxies. When we ask what existed before the universe, we are also asking where we ultimately come from. Perhaps the most remarkable fact is that the universe allows such questions to be asked, that it contains regions of complexity capable of reflection, that from a hot, nearly uniform state emerged stars, planets, life, and minds. Whether the universe had a beginning or has existed eternally in some form, this remains true. We are part of a cosmic story still being written. The Big Bang may mark the first chapter we can read, but it is unlikely to be the first chapter that exists. And as our tools improve and our theories deepen, we may one day discover that the universe is not a single event, but an ongoing process, one without a clear beginning or a final end. Until then, the question remains open. What existed before the universe? The answer lies somewhere beyond the horizon of current knowledge, waiting for the next generation of thinkers, observers, and explorers to bring it into the light.